Hello everyone and welcome to today's webinar, Maximum Performance, Minimum Effort, Intel Performance Libraries. Our presenter today is Noah Clemons, a staff technical consulting engineer in the Developer Products Division here at Intel. During this presentation, please send in any questions you may have, and we will get to as many of them as we can during the Q&A session at the end of our presentation. We now turn the time over to Noah.
Thank you. We're going to talk today about an area that some of you may know a little bit about, some of you may not know at all, but it's the fact that we've had a worldwide engineering team over the last 10, sometimes even 20 years work on hand-tailored optimizations for all of Intel processors that you can call on. I'm going to go into detail today on the many different performance libraries we have and how you can use them. Did you know that we have a vast collection of libraries that you can call on? The first one is the Math Kernel Library, which is heavily geared towards entire board optimizations. So what I mean by that is all the processors on the board, all the cores, and all the vector units. It's distributed multiprocessor aware, and it operates for a lot of mathematical functions in a lot of key domains. Next is integrated performance primitives, which is signal, image, media, and data processing functions that are heavily vectorized, from which you can do outside threading on top of that to scale across multiple cores. It's for those that really need a good single core optimization on a variety of different algorithms, as we'll talk about later. Threading building blocks is a C++ template library that allows you to express task-based parallelism, where you manage individual tasks rather than individual threads. It's a higher level way to think about parallel programming that lends itself to both advanced methods for parallel programming and simplistic methods for low-hanging fruit type parallelization opportunities. We also have a fairly new library over the last 2 years we've been creating called the Data Analytics Acceleration Library, which is similar to IPP and MKL in it's tailored functions for a data analytics pipeline. And then last but not least, we have an Intel distribution of Python from which you can call on several of these libraries to get additional optimizations for those interested in a more high-performance Python. Next we will go to Math Kernel Library. In this situation, you have a variety of highly optimized threaded and vectorized math functions that can optimize performance across any processor family that you'd like. It utilizes C and Fortran APIs with compatibility with a lot of older scientific computing libraries where you don't even have to do code changes if you're already calling on those libraries. It would just be a matter of swapping out the dependency, like for example, blas.h, you would use mkl_blas.h, and then it contains all these new hand-tuned optimizations that you can call on. It dispatches optimized code for each processor automatically without the need to branch code. So one call of the Math Kernel Library a few years from now, you can just swap out the dependency and it will contain optimizations for that processor line as well as ones around 10 years in the past. It has optimizations for that too. So what's new in the latest version of MKL is improved small matrix multiplication. So this is geared towards very large scale computations all the way up at the cluster level if you need to. But MKL is also branched out into embedded and IoT for those interested in different stream data applications or pushing computations as far as you can to the edge before you send it up to cloud. And so small matrices become more important in those situations. We've continued to work on distributed computation in the case of ScaLAPACK, 24 brand new math functions, simplified license structures, and additional distributions via other repositories that people like to use. So what's inside Math Kernel Library? Linear algebra, FFTs, neural networks, vector random number generation, summary statistics, vector math, and other different types of solvers. So this works across the entire Intel processor line with a wide variety of operating systems. And in the case of our embedded tool suite, System Studio works with many different embedded operating systems as well. Like I said before, we have automatic dispatching to tuned ISA-specific code paths. So if you notice here, you can have a code base that works across all of these different processors, but contains optimizations, in particular vector ISAs, as you move up in the generation. So we go all the way up to the latest Intel Xeon Scalable processor, to where, especially if you don't want to write AVX512 code, these MKL implementations already contain that. So you can focus on solving the problem rather than learning a new instruction set to write for. And of course, we also scale up to all these different cores and different threads. And we will continue to scale on top of that as processors increase cores and threads in the future. So how do we do this? We do core optimizations with vectorization. We do multi-many-core level parallelization. If you want to work if you have multiple processors on the same board, we can optimize across those processors as well. And this means you don't even need to specify that. It has probing to understand how to be distributed multiprocessor aware. And we have many different implementations for cluster scaling. We have a wide variety of materials online within the developer zone on how to get the most optimization out of these MKL functions, because the functions themselves are highly customizable as well, depending on your needs. Here's an example of different performance benefits that on automatic scaling according to the amount of threads. So this is single precision, general matrix multiply, double precision, and this is the same code base, but as you deploy to a higher number of threads, you get immediate performance scaling, especially as your problem size increases. We also have evolved with the times in the world of AI with deep neural network functions. So many of the commonly used building blocks for what they call DNNs are already included in the Math Kernel Library as a whole new wing of functions you can call on. Things like inference and training, image recognition, segmentation and object detection, and also the basic building blocks if you want to create your own algorithms. We have some of the best implementations on the planet of convolution, inner product, data transformation, and things like that. These are fully supported in TensorFlow, MXNet, the Intel optimization for Caffe, and we actually have an open source version if you'd like to get the implementation details of that as well, if you go on GitHub there. For those of you that have used Math Kernel Library before, here's a variety of enhancements. For many, many years, we've focused on the ability to turn on numerical reproducibility if you'd like. Math Kernel Library is highly composable with our threading library that I'll go into in the near future here. Like I said before, we have smaller matrix multiply enhancements, and besides that, the deep neural network convolution, normalization, and pooling primitives, things like that, we've made additional performance enhancements to. So next, we will move on to IPP, Integrated Performance Primitives. So these are highly optimized signal, image, media, and data processing functions. These are multi-core, multi-OS, and multi-platform ready, but they're essentially single core optimizations that you need to do the threading on top of that. We found over the years that is what our customer base wants the most, and generally for these types of algorithms, they know better how to scale across multiple cores, and what they really need from us as engineers at Intel are these optimized single core implementations that utilize the latest Symbian instruction set so that you don't have to spend a lot of time working at that low level of coding. The new aspects of the 2018 version are that we have new functions for LZ4, data compression and decompression. You can use GraphicsMagick to access IPP-optimized functions, and we have platform-aware APIs for 64-bit parameters with new ways of thinking about image dimensions and vector length. So here are the different types of functions that are in IPP. So there is a little bit of overlap with Math Kernel Library, but there's also a wide variety of aspects that Math Kernel Library does not have. So image processing, data compression, and cryptography are things that we've been implementing for many, many years. And what's interesting here is that you can call on an IPP function that will contain the optimizations for everything from Xeon down to Atom. But if you don't need or want all those optimizations, you can actually call an IPP function that's optimized for just one type of processor line as well. So we do have flexibility in that regard. So here's an example of AVX512 for image processing. This is the same situation here that I mentioned earlier, where you can have an IPP function that contains different AVX optimizations. In this case, we show the immediate speed up based on that optimization dispatching to different processors. Here is a similar example for data compression, to where we do boost versus original LZ4 and LZO libraries with different compression ratios. Bottom line is, if you're using IPP for data compression versus your own C-based implementation, we generally can beat that in some multiples that certainly make using this library worthwhile. So next, we will move on to threading building blocks. So MKL and IPP were individual functions that you call on. TBB is a C++-based template library with a wide variety of different things that you can call on. And I'll go into that in detail in a moment. So TBB, highly templatized C++ library designed to simplify parallelism and take advantage of all CPUs on a device or multiple different devices. So these are easy to use APIs, production ready, that allow you to scale without having to think too much about your scaling. It's one of our earliest libraries we've ever made, so we have a lot of experience with parallelism all the way back to when we were scaling across 2 cores at a time. So we have a free tools program, open source implementations of this, and also you can find this in Parallel Studio and System Studio. Since this is one of our oldest performance libraries, we have different applications. We found that so many different industries and applications find this useful. Just listing here, a lot of these people are in diverse areas but they all use the same type of parallelism, and they all use the same types of constructs that we all learned in a parallel algorithms class. So what type of applications need to be multi-threaded? This is where you can break the problem down into tasks that can be run in parallel, or the problem itself is massively parallel. So all these different seemingly diverse fields all use same type of synchronization primitives and all have the needs for different mathematical operations to spread across multiple cores, but perhaps someone in oceanography or astrophysics doesn't want to spend a lot of time distributing information across multiple cores, and they want to focus on science and different problems to solve. There are a lot of options in threading out there. Of course, you can thread yourself. There are other libraries on top of that, but let me explain some different advantages that TBB has. We are the only library that allows you to specify a task rather than manipulating threads with different levels of complexity. Whereas OpenMP is a few different keywords to express parallelism, we have many, many different options and levels of control to where you can map your logical tasks on the threads with full support for different types of nested parallelism. We have a flow graph feature that allows you to express dependencies to where you're thinking of problems as a graph rather than expressing it in a way that can be evaluated as a graph. So it's a way of saying these two things, for example, can be parallel, but not until this particular aspect happens. You can express that, either through, think of it like as a flow chart, but expressed as some sort of graph of dependencies. You can express all that through C++ templates and then have TBB process through that graph and pick different places that can be parallelized. We are finding over the last few years that started out to be an early testing feature, but now we're finding that large amounts of people are using that because it is so useful. Other interesting things here, high-level parallel algorithms and concurrent containers, and things like a scalable memory allocator, locks, and different atomic operations that are already implemented that you can call on. Here is an example of all the different features, the feature set for parallelism that you can call on. So generic parallel algorithms, I said before, flow graph, a set of classes to express parallelism as a graph of compute dependencies. What would be useful to the most amount of people are the synchronization primitives and different ways to allocate memory through what we call a scalable memory manager and false sharing free allocators. The way TBB works is through task scheduling, so we have a work scheduling engine that empowers parallel algorithms, and if used in context with a flow graph, it can take advantage of that as well. Here is a nice cursory view of the features and function lists. Synchronization primitives, like things as complicated as a speculative spin mutex, most people would not want to implement that themselves. You can rely on our many years of experience in parallelism to just have that implemented for you, so you can just express things in the way you want to express and not worry exactly how those things are implemented. Memory allocation, as I said before, very, very useful to a large amount of people because memory is something that can be easily, mistakes can easily be made. And it's nice to already have that set up where you can call on that. Here's just a nice quick graph that shows a variety of different algorithms using threading building blocks using the different APIs that we offer, scaled to arbitrary amounts of cores, to where in most situations here we're getting a speed up that is highly proportional to the amount of cores automatically. So the main takeaway from this graph here is that once you've used the APIs for threading, you get a lot of free scaling without you having to manage it much at all. Here's just a cursory view of how TBB works. We're going to have more in-depth presentations on threading building blocks through this tech-decoded website in the future. But this is just a quick view of that. This is the C++ library that provides what's needed for message-driven and fork-join tasking layers. So our way of setting this up is that it's tolerant of unanticipated CPU loads, and from there you have your threading covered. You can use the Intel compiler, your own compiler, or libraries at the third level to get the SIMD optimizations, the parallelism inside each individual core. Here's a list of the available compute resources that TBB can work with. So we have one threading engine under all the CPU side work, and this coordination layer that works with this TBB flow graph that's the glue connecting hardware and software and allows you to expose the parallelism between these different blocks. So now let's go into the Data Analytics Acceleration Library. So the name of the game with Data Analytics Acceleration Library is that these are all highly tuned functions tailored for classical machine learning and analytics. These use Python, C++, and Java APIs and connectors to other different sources, including Spark and Hadoop. We have a free and open source community supported versions that are available, as well as paid versions to where you can get access to an engineer on our team that can help you out with any aspect of your data analytics pipeline. Pre-processing, transformation analysis, modeling, validation, and decision making. We have functions that you can call on in this library that can help you in any stages of these pipelines. I highly recommend you see if there's at least one function in each of those categories that you can call on, and it could save you a quite bit of amount of time. What's new with the 2018 version? New algorithms, classification and regressions. We have Spark MLib compatible API wrappers, improved APIs, and a repository distribution via Yum, apt-get, and Conda. So how exactly does this library work? This does optimizations within one CPU core, just like IPP. So it doesn't scale across the entire board because generally people in data analytics know better than us on how they want to scale. So you could use threading building blocks to scale them to multiple cores or multiple processors or even many core architectures, or scale the cluster via many of the different methods that are out there, either the ones that we provide or other ones within the industry. So here's three ways that our library works: batch processing, online processing, and distributed processing. The key here is that if you get the library calls down, you can set up the library to work in any one of these ways without any issue. Here is a list of the algorithms that support these different types of processing. So notice here we have some that support batch processing and some that support batch, online, and or distributed processing. This is not set in stone. So if there's some algorithm here that you need to have the capability to do more than just batch processing, online or distributed, please let us know, and we'll look into making that happen for you. This library's only a few years old, so we're still, constantly improving it. We're definitely looking to get different customer feedback on how we can make this more applicable to your day-to-day data analytics lives. So here's some new aspects, again, mapped according to batch processing and batch, online, and or distributed processing. New additions are ridge regression, decision forest, decision tree, and KNN. Besides that, it's really worth your while to check and see what other algorithms we have in the case of regression, supervised learning, classification, unsupervised learning, and collaborative filtering. So what's new again? New classification and regression, decision tree and forest, KNN, ridge regression. We have the Spark MLib compatible API wrappers, improved APIs, and repo distribution via the three most conventional, most widely used repos. So last but not least, we're going to go into the Intel distribution for Python. So for those that are using Python in a more high-level sense, productivity sense, there still may be some aspects of the Intel distribution that you might want to use. For those of you that are looking for something very high performance and tailored for Intel processors, this is even more of a better fit. So we'll go into this in a greater detail, and then I'll go into some different aspects of Python that you may not have realized that we have and offer that may be very useful to you. So why would you want to use our distribution? We are a high-performance Python distribution, and we're well suited with, we have accelerated NumPy, SciPy, scikit-learn, well suited for scientific computing, machine learning, and data analytics. This is a drop-in replacement, so you don't have to change your code at all. It would be simply just using the Intel distribution instead. This also, if you get it in conjunction with one of our tool suites, Parallel Studio or System Studio, you can take advantage of priority support and get connected to our engineers for technical questions and enabling on your project. So what is new? We've updated to the latest version of Python. We have an optimized scikit-learn and different Conda recipes. And if you notice here with our performance graph here, the performance advantages from simple drop-in replacements are undeniable here. So again, what is inside and why would you want to do it? First things first, faster performance. We have accelerated versions. You have NumPy, SciPy, scikit-learn that use the very libraries I just talked to you about, MKL and Data Analytics Acceleration Library. This can scale with Numba and CPython, and it's optimized, obviously, for the latest Intel architecture. Greater productivity, so we have a lot of pre-built and optimized packages for many of the reasons people are using Python these days. We have great integration with Jupyter Notebooks, and it's a free download and free for all usage, including commercial deployment. We're very compatible with the ecosystem, and like I said again, if you need some commercial support, you can get this through our Parallel Studio suite, and I'll mention in a few minutes why that would be even more beneficial for you. So here's an example on how to install the Intel distribution. So notice it's very easy with a full standalone installer. You can get it through Anaconda, Docker Hub, and Yum apt. But remember I said that there were some extra advantages of the Intel distribution for Python and some aspects of it that you may not know about. So outside of optimized Python, how efficient is your Python, C++, or application code in general? Are there any non-obvious sources of performance loss? Performance analysis can give you the answer. So we have the capability to not only performance analyze C, C++, Fortran, and the use of libraries, not just our libraries, but anybody's performance libraries, but we can analyze Python code as well. So we'll go in, for the next few slides, we'll go into different aspects of how to profile Python code and understand how to tune what was originally created as a productivity language for performance. So you can tune Python and native code for better performance. So you don't have to use the Intel distribution for Python. You can use whatever you'd like. But it's nice to have a single tool that can profile your Python and native code in the same application via auto detection with mixed Python, C++ code and extensions, to where you can understand, even in line by line with Python code, your performance hotspots at the line level. Low overhead, you can attach and detach to a running application, and you can decide where to focus your tuning efforts for most impact on performance. The reason why this is highly relevant to libraries is that if you find a block of code where you need to spend most of your time, you could ask yourself, okay, I need to spend some time optimizing the next, this block of 20 lines of code. Could some aspects of that code be replaced with one of our many performance libraries? MKL, IPP, Data Analytics Acceleration Library, or could I use the TBB threading library to express some parallelism? It just helps you narrow down where to spend your time and try to use the tools that we have. You can diagnose your problem quickly and accurately because we have a true aspect of performance analysis that is unparalleled in the industry to isolate lines of code. And you can detail your Python calls into your native functions. So you can identify the exact line of code that is causing the bottleneck, and from there decide where to do. Is it use the Intel compiler to optimize it? Is it use some compiler flags to generate some tailored SIMD code? Is it write your own SIMD code? Is it call an IPP or MKL or data analytics function? All I know is that you would love to pinpoint where your problem is first so you don't waste time somewhere else. So here's another graph of a Python analysis where we have the call stack listing for Python and native code and a detailed time analysis to know exactly when these things are happening through the course of a run. So this means that you can say, I want to run this code for the next 20 seconds, and I want to see exactly what my utilization is across the board. What I just said represents a two-prong approach for faster Python performance. So you can always just use your own Python distribution, but if you use the Intel distribution for Python, you're likely to get some immediate performance benefits for the drop-in replacement via optimization for multi-core and the latest Intel processors. Next, you can actually use vTune Amplifier to profile that code. So you can use the Intel distribution for Python, you also don't have to. But bottom line is you're going to get a detailed summary of the entire application execution profile and auto-detect even with mixed code and low overhead. You want to detect hotspots accurately and get line level analysis. So this is available as Parallel Studio, Professional and Cluster Edition, and also within System Studio as well, our embedded in IoT tool suite. What's new for the 2019 beta of Python? So the Python community is rapidly expanding in capability. We have faster machine learning with scikit-learn functions, built-in access to the XGBoost library, and easier access to install. And so you can actually access the Intel optimized Python packages through any of these aspects. The Intel distribution for Python page, Anaconda Cloud, Python package index, Docker Hug, and Yum app repositories. So that closes this Python and libraries presentation for me. The bottom line is there's a lot of free performance on the table that you can get access to if you simply go on our website, many of our different web resources, and use them. We have many different programs and many different license structures, sometimes free, sometimes academic, sometimes commercial, that can suit your needs, and a worldwide team of engineers dedicated to helping you solve their problems. We don't tend to want to just throw these tools over the fence and you figure them out. We have people that can help you, as well as hundreds of knowledge base articles, videos, and how-to guides that can move you along the way to becoming a better high productivity and high performance programmer.
All right, for that presentation, and we have time, and several questions have come in, so let's wrap up this session by answering some of them. Let's see here. The first question is, how well will Intel MKL libraries work out of the box, and where can I find performance numbers?
All right. So that's an easy one. So if you just go on the MKL website, we have a section just for charts and competitors. As long as your code is standards conformant C++ or Fortran, these MKL libraries will run out of the box with great performance. In fact, that's one of the strong suites of MKL. I mentioned in the presentation of the immediate compatibility aspects, where in a lot of cases, if you're already using a scientific computing library in the past, you can just replace the regular dependency file with the MKL dependency file. A perfect example would be if you have a lot of BLAS, basic linear algebra subroutine codes, or functions calls. If you just replace the H file, the MKL replace BLAS.h with MKL BLAS.h, you don't even have to change any lines of code and get immediate performance benefits. So bottom line is, check the MKL website for different charts and performance numbers and benchmarks, and try to see how you can just swap out dependency files or just swap out quickly identifiable functions to get drop-in performance with MKL.
Okay, great. Another question, how are the libraries distributed? Are there non-commercial options? Where can I find them? And how is support tied in?
All right, so all of the performance libraries are free for both commercial and non-commercial use. So if you just type in Intel Performance Libraries, you can get them for all sorts of various OS configurations. If you purchase one of our tool suites, so System Studio or Parallel Studio, that actually comes with commercial support from Intel engineers. So we can actually, give live. You can actually submit a support ticket to us and actually send us code, and we can actually help you out along the way. So we have many different tiers of support, and at the minimum, you get forum support with our free libraries program.
All right, thanks. We've got time for about 3 more questions, so here's another one. What do I do to enable optimal performance on new platforms with Intel IPP?
So you can optimize for current and future platforms with IPP. So the way that works is with each new instruction set upgrade. A new processor comes out, maybe has a new SIMD instruction set. We add a new implementation layer. And what does that mean? We actually hand-coded an optimization for a new processor that you don't have to do. What happens with the other implementations? Those prior ones do work as before, but those functions themselves can benefit. The functions that can benefit from new hardware capabilities will be updated and validated before new architecture is released. So you can unlock increased performance simply by using the newest version in a recompile. In most cases, the performance boost is automatic, and so you can start utilizing new capabilities right away instead of interrupting your development cycle for a new optimization in that fashion.
All right, great. How do I use these libraries with Python, and can I use them with Anaconda Python distribution?
Yes, it's kind of a long answer, but let me give you the more technical details for that. So our distribution focuses on getting native code like performance from packages like NumPy, SciPy, and scikit-learn. We do this by linking with MKL and Data Analytics Acceleration Library. You can have additional performance through threading modules with our threading building blocks and different processor optimizations. We are collaborating closely with Anaconda, Nthought, and ActiveState to share our performance optimizations so that it's available through their distributions as well. There may be a time lag based on different release cycles with them, but you can download the specific Intel packages from Conda and pip even if you alternate Python distributions or CPython itself.
Great. And the last question we have time for, when would I use Intel DAL over Intel MKL for similar types of operations?
So that is a good question that shows that you looked at my slides pretty intently. So you notice that there was some overlap between our data analytics library and our math kernel library. And it is true that in some cases we overlap them because different domains need similar operations, especially core building blocks. Here's the good rule of thumb. MKL functions are suitable when the entire data set fits in memory because those contain the distributed multiprocessor aware optimizations. Our data analytics library can be good to handle situations when data is too big to fit in memory all in once. So we allow you as the user, application programmer, to chunk in data piecemeal and get a final result at the end. Another aspect is the compatibility. So MKL is just a Fortran and C API, but Data Analytics Acceleration Library provides Python, C++, and Java APIs. So keep that in mind. MKL is for everything that fits in memory. C++, C and Fortran. Data Analytics is for when it's too big to fit in memory, and you need to expand into Python and Java in addition to C++. So that would be it for that question.
Okay, Noah, thank you for today's presentation. Well, folks, that's all the time we have. Thank you, Noah, for today's Intel Performance Libraries presentation, and thank you to everyone for joining us. Please explore the Tech-Decoded website for more information on Intel Performance Libraries and other powerful Intel software tools, including how-to videos, articles, download links, to all of the tools Noah reviewed today and other resources to help you. Thanks to all of you for joining us today, and we hope to see you again down the road.